Hello, my name is Brian Chaplin, and I'm from the University of Illinois at Chicago. And the purpose of this video is to describe a technology that we call reactive electrochemical membranes and explain its performance for the electrochemical destruction of per and polyfluoroalkyl substances, otherwise known as PFAS or forever chemicals. PFAS are very stable organic molecules due to the very strong carbon-fluorine bonds. These compounds were used in various products and different applications, and they can pose significant health risks. For example, studies have shown that they are a possible carcinogen and can cause damage to the liver and immune system, just to name a few. As a result of these health concerns, the EPA has set health safety advisory levels of 4 parts per trillion for PFOA and PFOS, which are two of the most common PFAS. The structure for PFOA is shown at the bottom right of the slide. And the EPA is also reviewing other compounds to decide whether health advisory levels or drinking water standards should be imposed. One of the major contributors to contamination of groundwater on DoD sites is the use of aqueous film-forming foams, and these are used in firefighting operations as shown in the image at the top right. The technology that we are researching is a electrochemical oxidation method, which is a very promising technology for PFAS destruction. In order to remove these compounds from contaminated groundwater, a treatment train approach works best. So first we start with our contaminated groundwater. We can run that solution over what's called an anion exchange resin. This resin is going to trap the PFAS, and we can have our treated water come out the other side. However, the trapped PFAS, which is absorbed to the anion exchange resin, needs to be desorbed once the resin has reached its capacity. So we use a concentrated salt with methanol that can desorb the PFAS, and then we're left with a concentrated PFAS stream that's going to be in this salty water that contains methanol. In order to remove the methanol, we use a technology called distillation. We can then remove the methanol, and then we're left with a concentrated PFAS stream that contains this salt. This stream will then be treated by electrochemical oxidation, and electrochemical oxidation is much more energy efficient to treat these small volumes of concentrated PFAS instead of treating the contaminated groundwater itself. That brings me to the overall objective of our work, and that is to develop an efficient, robust, and low-cost electrocatalyst for PFAS removal using our reactive electrochemical membrane system. So the schematic here is showing a simplified version of this reactive electrochemical membrane. We show a molecule known as PFOS, one of PFAS compounds, going through the membrane. And then what will happen on the anode of this membrane is the destruction of PFOS to benign products like fluoride, CO2, and sulfate, ultimately giving us clean water.
One of the keys to the performance of the REMs is related to its mode of operation.
So now I'm going to discuss how we make these membranes. So we start with a TiO2 ceramic membrane, which is shown on the picture in the bottom left at the top. And we convert that to what's known as Ti4O7. So I'm showing the overall reaction there. We have TiO2, we add hydrogen gas at a very high temperature, over 1,000 degrees Celsius. That is taking some of the oxygen out of TiO2 and combining with the hydrogen to form water. And now what we have is known as a suboxide of TiO2 with a nominal formula of Ti4O7. You can see from the image at the bottom on the left that the color of the membrane changes from a whitish beige to a bluish black, and that also imparts very high electrical conductivity to the material. So now if we look at the picture in the center of the image, we can see how we were actually operating this. So we have our tubular membrane, which we're operating as what's known as an anode to form oxidation. We put a stainless steel rod in the middle, that's going to be our cathode. We flow water inside that membrane, and we then force it by pressure through the pores. So the image on the far right is showing a schematic of these pores, and we can think of these pores as a collection of microreactors and we can take advantage of all the internal surface area of those pores, and many times we can get very high conversion of a compound by just passing it through our membrane a single time. So what does this actually look like in a real treatment process? So what I'm showing in this image is what's known as a multi-stage operation. So we have 3 of these membranes operated one after another, otherwise known as operation in series. And so the image is showing that we're pumping our water, our wastewater, through the center of the first membrane, and we're recirculating that. A portion of that wastewater is going to go through the pores, and that's going to enter into the second membrane in this stage. So every stage that we go through, we remove more and more of the contaminants. And we may need 1 stage, we may need 2, 3, or even more to meet a treatment objective. So that's the beauty of this technology. It can be operated as a modular unit. So we can add as many as we need in series, as shown here. We can also add a lot of these in parallel. And this depends on the total volume of wastewater we're trying to treat, as well as the treatment objective. And all of these membrane units, these REMs, are powered by a DC power supply. So we can control the current or voltage that we apply to these membranes in order to fine-tune these for a given treatment objective.
So here we have an image of the experimental setup that we're using in the lab to test this technology. So this represents a single stage. We have our pump that's going to circulate the water through the center of the membrane. We have our potentiostat, which is shown in the bottom right. This controls the potential and currents. We have, of course, our tubular REM, which is the black membrane in the center of the image. We have our counter electrode, which is a stainless steel rod that runs through the center of that membrane. And we also have our back pressure regulator. So this is operating in cross-flow mode. We run the solution through the center, circulating that solution. A portion of that liquid is coming through the membrane pores, and that's known as the permeate. So we measure that over time to see the amount of contaminants that we are removing.